All right, so let's make some sense here of what I mean when I talk about continuous notions and discrete notions. And what do I mean by that? And what does it have to do with atoms and light and Bohr's explanation of these barcodes, otherwise known as atomic line spectra? Okay, so I want you to think about a ramp, right? So let's think about a ramp that you could walk up, and you could walk up this ramp to get to some place. So let's say there's point B up here, and you'd like to get to point B, and you're starting out at point A, and you could walk up that ramp to get there. And you would have the choice, of course, to stop at anywhere along that ramp. And so if we were measuring your height, for example, or in other words, how high are you as you walk up this ramp, you could be at literally any arbitrary position along this height. If I were to measure how high off the ground you've become, you could really be at any one of those positions. It's completely arbitrary. It just depends on where you stop as you walk up this ramp. Okay, so this is what I mean when I talk about a distribution being continuous. Okay, so it's continuous in the sense that there is no break there. You could be anywhere along this ramp. And for the longest time, we believed that the energy of matter was essentially continuous. In other words, those hydrogen atoms we've been talking about could have or emit any arbitrary amount of energy. You just sort of, heat it up a little bit or do something to it, and you can arbitrarily change its energy. And that's what we would have believed. This is what we would call the classical model of physics in this case. And specifically how it pertains to chemistry. However, what Bohr proposed was, because these atomic line spectra were so consistent, they would never change. In other words, these hydrogen atoms really never do emit yellow light, for example. It's just not part of its spectrum. Doesn't emit that color ever under any circumstances. So the new model is one that is essentially discrete. And so how that differs is we're actually going to get rid of this ramp and replace it with a set of stairs. Okay? And a set of stairs is what I would call a discrete distribution. In other words, what I mean by this is that as I walk up these stairs, in contrast to the ramp, I'm only ever able to be at very specific values of this height that I'm measuring here. So when I was walking up the ramp, I was literally able to stop anywhere I wanted, and I could have been at any height. It was arbitrary. This is what we call a continuous distribution. But when I'm walking up the stairs, I can only choose to be here, 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 or here. Of course, I could be at the very bottom and the very top, but the point is still the same. I have now a limited, finite number of choices in which I could stop. And so I can only be at those specific heights. So this is what we would call a discrete distribution. I, frankly, am just not able to be at some intermediate height between any of those two places. It's just not an option in this particular setup. Okay? And so what Bohr proposed was that maybe the energy of matter, and specifically we are talking about electrons here, he proposed that maybe the energy of matter behaved a little bit more like this set of stairs. In other words, maybe electrons could only have very specific values of energy and not actually any old energy that we chose. So if we assume that, if we say, well, perhaps the energy of a hydrogen atom, or specifically the electron in a hydrogen atom, can only be at specific places. So what would that look like? Let's try to imagine that. So let's separate this drawing and think about the energy of a hydrogen atom now. Let's draw a vertical axis where now instead of height, let's measure energy. And what Bohr proposed is that potentially there is some low or minimum energy state. Let's call this the ground state. So here we are, ground state. And so Bohr said, well, let's suppose that there is some ground state of energy, and perhaps my electron has other options, but they're not infinite options. They're not continuously distributed options. Perhaps there is another option, and maybe it's right here, for example. Let's just sort of be more or less arbitrary about where we write these lines, but Bohr proposed that maybe there is some other state above it, and maybe there is some other state above that, and then maybe there is some other state above that, so on and so forth. But maybe there is very, very specific states. And so perhaps my hydrogen atom could be at this particular energy if it's in the ground state, or it could be at this particular energy if it's in the state above the ground state, or this one, or maybe there's others. But the point is that these are specific and discretely defined. And this is very different than if the hydrogen atom could have any energy at all. If the hydrogen atom could have any energy at all, then it could potentially have this energy, at this position here, which it cannot. And the reason we know it cannot is because of this line spectrum. It's because of this emission spectrum that hydrogen has. It never emits an energy that resembles, this one, for example. It just never does. So we are forced to admit that the hydrogen atom can't possibly have that energy. And this is really the quantum model in a nutshell, so to speak. And we have Bohr to thank for it. And what we need to do now is attach a little bit more detail to this and a little bit more notational context so we can make sense of it. So the first thing we can do to do that is actually give these states some labels. And so what Bohr did was he labeled these states and he called them the principal quantum states, and he gave them a symbol N. So if we give these a symbol N, so what Bohr would have done is he would have said that this is the N equals 1 state, the ground state, the very, very lowest one. And subsequent to that, you would have the N equals 2 state. And then, you guessed it, the N equals 3 state, and so on and so forth. Now there may be more, but for the purposes of our illustrations here, this will be fine. And so Bohr said that there must be different states, different energy states, and he labeled them with a symbol N. Okay, and he called these the principal quantum states of this system. Now, how does this explain the spectrum that we saw before? Well, it's actually quite simple. The way that this explains the spectrum that we saw before is that Bohr reasoned that if we had an electron in this system, which I'll just sort of symbolically indicate here with my highlighter, the hydrogen atom naturally, as all matter, would want to be in its lowest energy state. That would be the state that's most stable. We're all most stable when we're in our lowest energy state. So naturally, hydrogen atoms would tend to be in their ground state. So we would have an atom as being in its ground state. But if we were to provide energy to this system in some way, and we can provide energy to this system in all sorts of ways, but suppose we're talking about the hydrogen atom discharge tube, and we're sort of providing it with a lot of electrical energy. What could happen, and there's a series of things that could happen, but what could happen is that this electron could be excited and bumped up to one of, in principle, any one of these other states. Okay, so according to the diagram I've got drawn here, if we were starting out in the N equals 1 state, I have 3 options. I can be excited up to the N equals 2 state, I could be excited up into the N equals 3 state, or I could be excited up into the N equals 4 state. And of course, if there were other states, I could be excited up to those states as well, but for the purposes of our example, let's just consider these 4 in total. So what this really is, it's an absorption of energy, right? So my hydrogen atom, if in the ground state, can absorb energy to be then in n equals 2, n equals 3, or n equals 4. So it's an absorption process. So as I absorb energy, I get excited and I get raised up to a higher energy state. Now, if I'm left to my own devices at that particular point in any one of these states, and I'll just change color somewhat arbitrarily here, if I'm in, say, state 2, if I've been excited into state 2, then naturally I could easily emit energy. I could easily fall back down, so to speak, into the ground state. And so here's the interesting thing here. If I am in state 2, and this is according to Bohr and his hypothesis about how to interpret this line spectrum, if I'm in state 2 and I fall down to the ground state, I absolutely must have lost energy. Right? I used to be in the n equals 2 state energy. Now I'm in the n equals 1 state energy. So what happened to that energy? And it's Bohr's supposition that that energy gets released as a photon. And I do not, it's unfortunate that this line is written in green. I'm just trying to distinguish it from the blue ones. I'm not proposing that this photon is a green photon. I'm just saying that the atom could lose specifically that amount of energy and emit that amount of energy as a photon. Okay? Now this is interesting because we already know a bit about how to figure out the energy of a photon. So how would that relate to this atom? Well, if we're saying that my atom was in this n equals 2 energy and it fell back down to my n equals 1 energy, then I have just figured out exactly the amount of energy that that photon must have. If I started in 2 and now I'm down in 1, I know precisely how much energy I lost. So this change in energy between these two end states must be the energy of my photon. In other words, the energy of this photon as it is emitted from my system has to be the same, logically, as the difference in energy between the two states that the atom transitioned between. Okay. Now, likewise, I'll use a different color here, somewhat unfortunately, but likewise, I could have potentially been in state 3, and if I was in state 3, perhaps again I fell down to the ground state. If I did, I would, of course, also emit a photon, right? There would be no reason why I shouldn't emit a photon. And let me try to be just a bit more technically correct. If I was in state 3 and I fell back down to the ground state, I could have emitted a photon. And what I'm proposing here is that photon that I would emit if I was in state 3 and dropped all the way down to state 1 would have a greater frequency or a smaller wavelength. And the reason I'm saying that is because this is a greater energy difference, isn't it? Starting out at n equals 3 and going all the way down to n equals 2, that is a bigger delta E. That is a bigger change in energy. So there would be more energy associated with the photon that I released or emitted as a part of this process. So the energy of this particular photon would be higher. This would be a more energetic photon, and it would be associated to that new delta E, where I'm associating these energies by color, not by notation. So, E photon is written here twice, but the gray one is clearly different than the green one. All right, so I think at this point we can see that there are actually many options. For example, I could have been, and I'll just choose a different color yet again, no significance to these colors per se, other than they're just indicating different processes. But potentially I started at state 3 and maybe I just went to state 2. I could have done that as well. And this is really the crux of Bohr's argument. Bohr is really just arguing that, look, there must be these specific quantum states, these specific states that he's labeling with the letter N, and once we define those specific states, now we have all of these different transitions that are available to us And in particular, if we're talking about the light being emitted from atoms, then really what we're doing is we're talking about an emission process, which means we start at a high energy state and we go down to a lower energy state. And I've indicated 3 different options here, the pink one, the green one, and the gray one. But you can see that there would be many more. I could start at 4 and go down to 3. I could start at 4 and go down to 2. I could start at 4 and go down to 1, so on and so forth. And all of these different options are available to me, and each and every one of them would emit a photon, and here's the punchline here, of a very specific energy. So for example, if I did this 3-to-1 transition, as we're proposing I would, this one in gray, then that energy difference between state 3 and state 1 is always the same. That is always the same energy difference between these 2 different states. So if I happen to be excited into the n=3 state, and if I happen to relax back down to the ground state, I will always give off this particular photon. Somewhat unfortunate that I circled it in pink, so let's circle it in gray. I will always give off that particular photon. In other words, I will always give off that particular color. And so if we go looking at the hydrogen atom spectrum, for example, like this image here, notice that we always give off this red photon. We always give off this green one. We always give off specifically this blue one and this somewhat more purple one. And so this is why Bohr's model matches experiment, right? If we propose that our matter exists in these finite energy states, then as matter transitions between these energy states and it goes from one n level to the next n level, there will always be a very specific amount of energy associated with that transition. And so not only will the photons that are emitted from a piece of matter be the same every time, but there will be really well defined, really consistent. So the transition between n=3 to n=2 will always give off the same photon. Okay, and so this really was a revolutionary idea at the time, and this is really the crux of quantum mechanics. This is what quantum mechanics tells us. It really just stresses the fact that there are these specific energy states that we believe matter exists in. And in particular, I want to be clear, I'm talking about electrons in this particular case. So electrons, and the hydrogen atom has 1 electron, so it's the simplest case for us to think about and the simplest case for us to talk about. The hydrogen atom has 1 electron, and we're envisioning that this electron can be in any one of these n states. It can go up, it can go down. If it goes up, that's an absorption process. So the hydrogen atom can absorb light, but it can only absorb light of those particular energy gaps. So hydrogen will only ever be able to absorb light if the photon that is being shone on that hydrogen atom matches, if the energy of that photon matches exactly any one of these deltas. And I really want to be clear about that. It really could be any one of these deltas. It could be this delta, and you know, if my atom's in the ground state, it'll be bumped up to number 2. It could be this delta, and if my atom is in the ground state, it would be bumped up to number 3. It could be this delta. The diagram's getting a little messy now, but my point is you can go from any state to any other state. And if you want to go up in energy, that would be an absorption process. And so we know exactly which photons can be absorbed by hydrogen using a model like this. And we know exactly which photons can be emitted from hydrogen using a model like this. And they happen to be the same, right? They happen to be the same. So in our discharge tube example, the one that we've been talking about a little bit, the one that you'll be experimenting with in lab, what is really going on here is our elements inside are being constantly bombarded with energy, right? They're plugged into the wall. They're being constantly bombarded with energy. So all of the hydrogen atoms that were originally in the ground state are being being energized and being bumped up. And remember, there are billions of atoms in this system, so they're being bumped up to all of the states. They're populating all the states. Some of them are in state 1, some of them are in state 2, some of them are in state 3, and more and more and more, and they're all being bumped up. And just as quickly as they get excited and jump up to an excited state, all matter wants to relax. So it gets excited and then relatively quickly relaxes back down to the ground state, releases a photon in that process. Maybe along the way it relaxes from, say, state 4 to state 3, and then maybe it goes from state 3 to state 2, and then maybe it goes from state 2 to state 1. And so all of these photons are being released continuously in this process as the discharge tube remains on. And so what we get is this very characteristic spectrum. And so we're always seeing these red ones, which is symbolic of certain transitions happening in this discharge tube. But then also we've got the green ones, the blue ones, and the purple ones, so on and so forth. All right, so let's put the finishing touches on this theoretical model that Bohr came up with. I've copied this energy diagram over that we were talking about before, where we've got the first 4 n states indicated on an energy axis, just to sort of give us a conceptual picture. You'll notice I was actually very careful about how I arranged these. I put the ground state at the bottom, which is obvious, and then I spaced out number 2 a little bit, but then I spaced number 3 not so much above number 2 compared to the distance between 1 and 2, right? And then I put 4 a little bit closer to 3 than I put 3 to 2, so on and so forth. So that in principle, these states are sort of getting closer together as I go up. And I was very deliberate when I did that, although Bohr wouldn't necessarily have known immediately that these were specifically the energy states that we had to indicate. You can figure it out. And the reason you can figure it out is because the hydrogen atom emission spectrum that we've been talking about for a while here is spaced out in a very similar way. Okay, and really what you can do is you can say, well, there's a red photon here. Okay, so there must be 2 states, and maybe I don't know which 2, but there must be 2 states in the hydrogen atom that are different in energy by an amount that's equal to a red photon. Okay, so we know the energy of a red photon. We could measure, what the wavelength of this photon is using a technique much like you're actually using in lab this week. So we could measure the energy of this photon, and we could say, well, there's got to be 2 states somewhere that are different by this amount. And we could do the same thing with the green one. So the green one's a little bit more energy. Okay, so there's got to be 2 states over in the hydrogen atom that are different by at least this green amount. Likewise with the blue, likewise with the purple. We know that there's 2 states somewhere that are different by those amounts. And if you continuously put that information together, you'll eventually, complete the puzzle where you figure out where all of these different energy states are. And so that's an exercise that really anybody can do, and Bohr would have done that, and he would have, found this particular relationship, and you can actually come up with an equation to match this exactly. And so specifically, what we would have discovered by doing that is that the energy, and I mean the very specific energy of a particular n state, so you tell me which n state you're interested in, and that would be the energy of this. So it could be the energy of 1, the energy of 2, 3, 4, you pick the state. And the energy of this state, as Bohr discovered, was related to a constant value. And so this constant is minus Planck's constant, which we've talked about before, multiplied by the speed of light, which we've talked about before, multiplied by this constant called Rydberg's constant. Okay, and we can talk about that in a minute, but nonetheless, it is just a constant number. And then after the constant comes the interesting part, 1 over n squared. Okay, so this is 1 over n squared, so it's what we call an inverse square relationship, and it's precisely this inverse square relationship that produces this series of lines that get closer together as you go up. So the spacings get more and more narrow as you go up in energy states, and it's exactly because of this inverse square relationship that happens. So now that we have this, we're really armed with a very powerful tool here. We can predict precisely what the energy is for any one of these different n states, which allows us, perhaps more importantly, to actually predict the difference, right, or the delta energy. So what we really would like to know is, what is the change in energy between any two different end states, right? Because we know that the change in energy between any two states will be exactly equal to the energy of the photon that is either absorbed or emitted as part of that process. So if a photon comes in, I will absorb it if it equals the change in energy of two states. Likewise, if I go from some high energy state down to some low energy state, I will emit a photon that is exactly equal to that difference in energy. So what I'd really like to know is what is this difference? And I can do this because I know what the energy of any particular end state is. I can get the energy of one of them and then the energy of the other and take the difference, right? And so if I do that, what does that look like? Well, we always think of deltas in science as a final state minus initial state. So really what this is, it's the energy of whatever my final state is, so I'll put a little NF on that, minus the energy of whatever my initial state is. So this is the energy of end state I, so whatever the initial end state is. So if I go from state 4 to state 1, then my initial state is 4 and my final state is 1. And I can calculate the energy using this equation over here, okay? But I can express it, I can write it out in terms of algebra just by saying that this will again be my minus HCr, okay? So those constants, and we can talk about those constants later, but they're given. And I have to do my 1 over n squared piece, but I've got two different states. So I've got, again, the energy or the n value of my final state, don't forget the squared, minus the n value of my initial state squared. And so that will allow me to calculate very specifically what is the difference in energy between any two states. So it's a very valuable relationship here. Now, if you were to go ahead and get the energy of each state individually and then take the difference, you'll get exactly the same thing. So that this equation is really exactly the same as the one above it. But what this allows us to do is calculate the difference in energy between any two states of the hydrogen atom so far, which allows us to equate that to the energy of a photon, right? So we know that the energy of a photon, as we described earlier, is equal to either h nu, if I want to talk about it in terms of frequency, or it's equal to hc over lambda if I'm interested in talking about wavelength instead of frequency. So all of these things can be interrelated, and you can go from the wavelength that you measure in that hydrogen atom line spectrum to the energy of that photon, which then allows you to predict the exact difference between any two energy states. And so really at the end of the day, the fact that these barcodes exist for specific atoms is really the evidence, right? We talk about evidence in this class. Those barcodes are the explicit evidence that we have that suggests that matter, specifically electrons in this case, exist in these finite discrete energy states. And we can jump back and forth between any two of those states, but we can only jump back and forth between any two of those states, which means we have very specific amounts of light that we can emit and very specific amounts of light that we can absorb. And knowing what those specific photons are allows us to learn so much about the different energy states of matter that we have. And that's why facilities like the Canadian Light Source can help us learn so much about materials and biochemical properties and all kinds of amazing innovations coming out of right here in Canada. So stay tuned for more information on this, but that is fundamentally the connection between light and matter, and it's an important one.